The goal of this section is to be able to do the reverse of something that you've probably done quite a few times in terms of both variable expressions and just fractions. So let's start here with an example that hopefully you understand one direction of, so we can start getting some intuition for why we might want to go the other direction. Let's say we have 1 over x minus 1 plus 1 over x plus 1. And if we want to pull these two terms together to be able to write it in terms of one piece there, we need a common denominator. That is, we have to take that and multiply the top and bottom of the first term by x plus 1 in order to match up with the x plus 1 in the second term. And then in the second term, we'd multiply the top and bottom by x minus 1 because we'd need to make sure we're matching up with the denominator of the first term. So we would end up having x plus 1 plus x minus 1 over x squared minus 1, or 2x over x squared minus 1 as our equivalent expression. And that's fine as it is, but what we're going to work on here is how we could go in the other direction. That is, how I could start from something like 2x over x squared minus 1 and get to something like 1 over x minus 1 plus 1 over x plus 1, where we're assuming we haven't done all the work to go in the other direction first. And maybe if you're clever, you could probably guess how to do that. You can just push some numbers around and maybe you'll end up there by luck. But it's a math class. You want to be a little bit more exact. You want to be a little bit more, let's say, clever, where yeah, the reasons for why you might want to do this are probably a little bit murky right now. It's probably not very clear why you'd even think to do that, but just understand that if you go further with these things, there are a lot of cases, in particular with special kinds of sums, where being able to have two smaller terms is a lot more manageable, it's a lot more useful than having the one big thing. So let's be pretty general here. Let's say we have some function r of x is a rational of form f of x over g of x, where in particular the degree of g is bigger than the degree of f, where this is what's called a proper rational function. In the sense of a proper rational being something like 4 over 9, you get the bigger thing on the bottom. We're thinking that way here as well. So point is no long division because g is bigger. You can't divide a small thing into, well, you can't divide a small thing into a big thing. Yeah, so I want to say that. It's clunky, now I'm trying to say it out loud, but that's our setup. We've got more terms on the bottom, more bigger terms on the bottom for that matter, where we'll say in particular we have that g can be factored. G of x is equal to two other parts, g1 of x and 6. Let's level that off just a little bit more. g2 of x. And for simplicity's sake, we'll say it's just those two factors, but if we had a g3, g4, g5, g6, it still works for the same sorts of reasons. It's just the whole thing would get a lot more complicated. So I'm going to stick to the two factors case here, where using what's called the Euclidean algorithm, it's a little bit outside the scope of this class, but we've seen things that more or less build off of it before. What we can do is take this and say that because we have those factors g1 and g2, we could say that 1 is equal to g1 of x times some other polynomial p of x plus g2 of x times another polynomial q of x. This is kind of like the division algorithm, but it's sort of a twist on it in terms of having a 1 over there to shift things around a little bit. And again, that doesn't seem like it helps us at all. But we can take this another step further. We can take this into another direction if we divide both sides by g. Because if we divide both sides by g, we can recognize that over here we would have 1 over g. And on this side, we're dividing all of this by g. We can split our parts up, where if we divide this g1p, then g underneath that's going to cancel the g1, and we would be left with p of x over g2 of x plus, over here the g2 would cancel, so we get q over g1. And from there, circling back to where we started, if we multiply in an f, then we could say that r of x, which as we originally defined, is the proper rational f of x over g of x, that can instead be written as f of x times p of x over, oh, excuse me, I made a mistake. All right, no, I'm still good. Yeah. Overthinking things. There's too many g's here. It's confusing me a little bit too. Don't worry about that. That's not a little g there. This should be that g2 factor. And then in this part, we have f of x times q of x over g1 of x. And we're going to see more about how we define the exact flavor here of what things like fp and fq look like. Don't worry too much about that right now. But the point here that we're getting, the point that I really want to make sure we see, is that if we have something in this rational form, we can always split it up if we take care how we do it in terms of the factors of the denominator, in terms of what's on the bottom there, where our goal is to properly define these fp and fq things so that they match up, where for the sake of simplicity, we have a couple of conditions we want to meet here, that we want all of the factors on the bottom to be irreducible for the sake of simplicity. If we put something in there that has more complex terms, it might cause some problems later that we don't want to deal with. And then our other condition is that the numerator always has to be of degree 1 less than the denominator to account for any possible factors. So, when we're making this fp up here, that has to be 1 less than g in terms of degree, but we're going to make it as general as possible to make sure that we have every single thing that could be up there fitting to still make it work in terms of a, that's what I'm looking for, proper rational function. And this process, the process of splitting up rationals in terms of the factors of the denominator, is what we call partial fraction decomposition, where we're going to see a few cases here for how that works, and in particular I'm going to focus on the most basic cases where our denominator factors into linear parts. And we're going to see that first next with the most approachable case when it factors into unique linear components.